Okay, folks, today this is just going to be a short video, but we want to have some fun every once in a while. And today is going to be one of those fun exercises. We want to take some of the formulas that we have encountered and derived and bring them to bear on a practical question, a practical problem. So we're going to do some problem solving, and we'd like to figure out how much of an effect will light actually have on a photoresistor. A photoresistor, we said, was nothing other than basically a piece of undoped, say, silicon, right? Just a crystal, a little crystal of silicon. And when we shine light on it, we said we can we can increase its conductivity by quite a bit. But we'd like to quantify that, and we'll want to do a sort of a sequence of steps today to see if we can derive a formula based on all the things that we've said. Okay, and so the emphasis will be on comparing to something that we could in the end measure and verify experimentally, right? So we don't want to just have this in the realm of abstraction. We'd like to manipulate things mathematically to the point where quantities appear in these formulas that could be directly measured. Okay, and so that is our goal today. This is our problem solving challenge. So here we are, we're looking at a photoresistor, and we want to say something about its photoconductivity. So where do we start? Well, let's start with a little sketch here, right? We said that the photoresistor was maybe just a little piece of silicon crystal, right? And then when we shine light on it, then it's going to conduct a lot better. And the reason, of course, is that, as we'll see, but the qualitative or conceptual reason is that we are able to promote electrons from the valence band into the conduction band by absorbing some of that light. Okay. So also notice that we're going to bring in this particular dimension of the crystal, the thickness, namely D. All right. So without the light present, so if we block the light, we know that we have a formula from before that we derived, namely Ne mu, okay, in general, is the conductivity, sigma. So over here we have conductivity, and here we get this Ne mu combination. Now, of course, when light is absorbed and an electron is promoted into the conduction band, well, it leaves behind a hole. So one thing that happens is when a photon is absorbed is that we create an electron hole pair. And so I have to sort of augment this formula to accommodate that, to model that, right? So we have these electrons in the conduction band, but we still also have then these holes in the valence band, right? And so that is not a new formula. We've derived it before, and that's going to be our starting point, right? So I can say that these numbers here are the same because light always creates these things in pairs. Okay, and so I can factor that out, and I'm going to be left with E times that number times the quantity mu E plus mu H. These are the two mobilities added together. Okay, so now what's the situation with light? Well, first of all, without the light, then why do we get any kind of electron hole pairs at all? Well, in that case, those are thermally excited conduction electrons, right? So they were able to, they would just happen to have enough thermal energy to make the jump. Now, at room temperature even, that's not very likely, but since we have so many valence electrons, there are going to be some conduction electrons, even though, the probability is pretty low. So this N naught here refers then to just to sort of the thermally excited electron hole pairs. But then on top of it, when we shine the light on this silicon crystal, we get additional pairs from the absorption of the photons. And so now our conductivity should just go up even more, right? So we have this normal, sort of dark, you could say, conductivity, and then we add this factor to it, E times the change in electron hole pairs, so that the addition in electron hole pairs due to the light, okay, times combined mobility. Okay, so here's the formula again. And so if I then think in terms of a ratio, and when I shine the light on this crystal, by how much does it conduct better than before? So in terms of a fraction, you know, not in absolute terms, but in relative terms, this delta sigma over sigma naught, well, that gives me then, the nice thing there is then everything sort of cancels out. The mobilities cancel out, the E cancels out, and I'm just really left with the delta N over the N naught. And so, of course, for a photoresistor, I would like to make this as big as possible, right? I would like to make that difference as large as possible, because that's sort of the contrast that we get. All right, so can we estimate this delta N? Okay, what does it depend on? Remember, we said we wanted to chase everything all the way back to quantities that could be directly measured. So delta N is not a quantity that can be directly measured. And so we're not done yet. This is not our last step here. We need to go down that rabbit hole a little bit further. So what does it depend on? Okay, so here's a dynamical equation for N. Okay, and so it's a first order differential equation. What I'm saying here is, how can we change the N? Right, so it's a time derivative with respect, of N, a time derivative of N. So how can we change the N in time? Well, we can create new electron hole pairs. That's got to be the G. And then what's this term here? Well, it has a minus sign in front of it. So that must be some reverse process. So this G here is the rate of electron hole production by light, right? We're absorbing photons and we're producing these electron hole pairs. So that's going to be the production. And then the minus term, the negative term, well, that term has to be the rate of destruction of electron hole pairs, or we're going to say the rate of recombination. When an electron fills a hole, okay, the two recombine. And so that's called recombination. And so that recombination term, rate, it's a rate, right? That recombination rate, well, obviously it should depend on how many pairs we have above normal, if you will, okay? So how much more, how much larger is N compared to N naught? If N is equal to N naught, then we're good. We don't have to change anything. But if we're significantly above the dark numbers and not, then we get this recombination to kick in. How fast does it kick in? It takes a time that I'm calling T prime here, or tau prime rather, tau prime. Okay, and that is the characteristic recombination time. Okay, so you should see that the dimensions sort of work out as well, don't they? I have a numbers per second here, I get a numbers per second here. And this is also a rate here. This G is a rate at which these numbers of pairs are produced. Okay, so here's our equation, but for steady state, okay, in the steady state, we know that things can't change. We've reached a plateau, the numbers don't change. And so setting the previous right-hand side to 0, we get that the delta N is going to be related to these other constants in the following fashion, right? The delta N is equal to G times tau prime. So the G here relates back to the production due to a photon absorption, and then the tau prime relates back to the disintegration or the recombination of those electron hole pairs. Okay, well, that's an interesting formula right there. So again, we're not anywhere near measurable quantities yet. Okay, so we have to chase it down further. What is G? Okay, what is G in terms of something that we might be able to measure? G right now just has the meaning of a rate of production of electron hole pairs. Okay, but and since light produces it, it must have to do with how much light there's incident on the silicon crystal. Okay, so here comes this next formula. G should be proportional to how many photons hit the silicon per unit time. And here is the most important factor, right? This n photons over delta T. How many photons per unit time actually hit the crystal? That's the reason we get any additional electron hole pairs to begin with. Yeah, and so, but then that can't be the end of the story, because not every single photon would be absorbed, right? Some of the photons may go right through the crystal and not be absorbed. And so we have to also factor in the absorption coefficient, alpha here, right? So if we go through this formula, you can sort of see that it really does make sense. Okay, we get the absorption coefficient, we get the thickness of the crystal. Okay, the thicker, the more of these photons would probably be absorbed. We get the light intensity. It's not really the light intensity per se, but proportional to the light intensity, number of photons per unit time. And then they're all divided by the volume of the crystal. So you might ask, why do we divide by volume? Well, these little n's are all per unit volume as well, right? So it is necessary to divide by volume to get it on an equal footing. All right. So number of photons per unit time is, again, not something that can directly measure. What we can directly measure with an instrument would be the intensity of light, right? But the two are clearly related, because the higher the intensity of the light beam, the more photons per unit time I get. And so clearly this will depend on the intensity, but it also depends on the cross-sectional area. So, and in this case, it's the cross-sectional area of the silicon crystal, assuming that the entire crystal is illuminated. And that gives you then, well, the intensity is what? In watts per square meter. That's how intensity is sort of defined, at least dimensionally, watts per square meter. I multiply by a cross-sectional area, and that gives me meters squared. So now I'm left with watts. But this here, okay, measures numbers of photons per unit time. Here we have watts. Okay, so that's joules per second, joules per unit time. And so here I still have to divide by the energy that each photon carries, h nu. And then I should get the number of photons per unit time. So here you see I'm casting it in terms of quantities that are more directly measurable. The intensity I can measure, the cross-sectional area I can measure, and the frequency of light that I'm using, I can measure that. And h is just Planck's constant. So we can plug that back in to this equation. Okay, and I'm going to just, for simplicity, call the intensity I and the cross-sectional area A. If I plug that in, then I get something like that. Okay, and so something nice happens, of course, here, because we had a D waiting out here. Now I'm multiplying it by the cross-sectional area. That's nothing other than the volume of the crystal. And so that cancels out, and I'm really left with a fairly simple expression here, alpha times the intensity over h times nu, the frequency. So that's G. And so finally, I can plug that expression for G back in, and I get that delta N here is given by this formula, namely the absorption coefficient times the intensity of the light that I'm using, the light source I'm using, here is my tau prime. That is the rate at which recombination happens. Okay, and then I divide that by the photon energy h times nu. And so with this delta n, we can then plug that back in, right? We can use that expression and substitute it into the original formula for the fractional change in conductivity, delta sigma over sigma naught. And we get a final answer out for our expected effect. We're getting an answer out for the change in conductivity, the fractional change in conductivity of the photoresistor, okay, based on things that I can possibly measure. So the only thing that might be a little bit tricky is this T prime, of course. That is not directly measurable. So that is the only thing that I might have to estimate more heuristically. But aside from the T prime, everything else I should be able to have direct access to. Of course, this delta n here would still have to be divided by the n naught in order to get that fractional change. The n naught, on the other hand, we have a formula for, right? And that formula is mostly sensitive to temperature. And so the temperature will factor into this fractional change, because the higher the temperature, the more intrinsic electrons I get in the conduction band, right? I strengthen the intrinsic effect. And so, but if I know the temperature at which I conduct this experiment, then I can fairly easily estimate the n naught. Here's a formula that gives you the delta n. I take the ratio and I get something that's very easy for me to measure, namely the delta sigma over the sigma naught. Right, delta sigma over sigma naught. It's a straightforward measurement. Basically, I measure the current for a given voltage. Okay, so there we go. So hopefully this was helpful. We were able to start from a formula that seemed pretty abstract, but we ended up somewhere where we can actually estimate this thing. Okay, and so there's going to be a homework problem where I have you sort of put into this formula realistic numbers. Okay, so see you all on Wednesday.